What if the most impenetrable wall in the universe isn't a wall at all, but a ledger? A book that records everything that falls into a black hole, not by erasing it, but by shuffling it into a hidden, whispering pattern on the boundary of spacetime. Black holes have long been painted as cosmic wrecking crews that erase information as if it never existed. Then quantum theory, which loves to insist that information is never truly lost, crashes into that image like a chorus of skeptics. The result is a paradox so provocative it has driven decades of debate: the Entropy Horizon Paradox. If information survives a black hole, how is it stored? If it's stored, how do we ever read it back? The questions aren't academic riddles. They touch the very blueprint of reality. Before Hawking, the prevailing picture of black holes was simple and stark. You plunge through the event horizon, and whatever you are, dust, light, thoughts, vanishes beyond no return. General relativity described the horizon as a point of no escape, a one-way surface. Information, in the eyes of classical physics, appeared to be lost forever. Then came Jacob Bekenstein in the 1970s with a bold bound. Entropy, a measure of information, scales with area, not volume. The intuition was strange but powerful. The boundary of a region might store its secrets. Stephen Hawking's calculations in 1974 added fuel to the fire, predicting that black holes aren't perfectly black, but radiate faintly, emitting what we now call Hawking radiation. If a black hole can evaporate, can information really vanish as it fades away? The first whiff of a paradox had appeared. A quantum universe cannot simply erase information. There must be a way that the radiation encodes the past. Yet the radiation appears thermal, blind to the specifics of what fell in, as if the book's pages were shredded to ashes. The stage was set for an extraordinary chase across theory and mathematics. The core mechanism lies at the crossroads of gravity, quantum theory, and information. Black hole entropy, encapsulated in the Bekenstein-Hawking formula, ties entropy to the surface area of the horizon. Think of the horizon as a two-dimensional library wall, each microstate a tiny imprint that collectively accounts for all the possible configurations inside the black hole. In this view, rather than a colossal gobbler of information, a black hole is a storage device with a staggering efficiency. Its information capacity grows with area, not volume, hinting at a holographic principle, the idea that a higher dimensional reality might be encoded on a lower dimensional boundary. The real turning point came from asking not just what the black hole does to information, but how an outside observer could ever see that information again. Hawking's thermal radiation implies that the details of what fell in are lost, swallowed by the abyss. But quantum mechanics insists on unitarity. The total information of a closed system remains, well, total. If Hawking radiation is the only channel by which a black hole communicates with the outside world, then that radiation must gradually become correlated with the interior's past states. In such a universe, the black hole's interior isn't a separate, inaccessible region lurking behind the horizon. Its information is embedded in correlations on the boundary, radiating away into ordinary quantum fields. That realization is more than a trick of equations. It suggests that spacetime, geometry, and gravity themselves may arise from quantum entanglement patterns on a distant boundary. The deeper story is even more intricate. The information paradox pushed theorists toward bold, sometimes uncomfortable propositions. One idea is black hole complementarity. Nothing dangerous about a single observer's viewpoint, because no observer can see both the interior and the Hawking radiation at once. The firewall paradox later challenged this, arguing that maintaining unitarity might require a searing boundary at the horizon that would incinerate infalling observers, a dramatic violation of the equivalence principle. The debate wasn't merely philosophical. It sharpened questions about locality, entanglement, and how information could be encoded in the quantum structure of spacetime. In recent years, a richer chorus has joined the conversation.
Soft hair,
The idea that black holes can carry subtle, low-energy excitations offers a mechanism for information to thread onto the horizon without violating known physics. The island paradigm, developed in the last decade, suggests that part of the black hole's interior is effectively included in the entanglement wedge of the Hawking radiation. Put simply, the information can be retrieved from radiation as if a portion of the interior becomes islanded in the outside universe. This isn't a magical loophole. It's a reformulation of how space-time geometry and quantum information intertwine. Replica wormholes, a sophisticated mathematical device, provide a path to compute the page curve in a way that preserves unitarity, showing that the entropy of radiation can indeed decrease after the page time when the black hole shrinks. The paradox, once a stark contradiction, is gradually dissolving into a tapestry of ideas where information survives, encoded in the geometry of horizons and the global pattern of entanglement. The broader implications stretch far beyond black holes. If information is preserved by holographic encoding on a horizon, then reality itself might be a grand hologram, where the bulk properties we experience are shadows of deeper, boundary-level dynamics. The entropy-area relationship hints that space-time isn't a fixed stage, but a dynamic emergent construct shaped by information. This reframes questions about locality, causality, and the ultimate degrees of freedom of the universe. We are moving toward a worldview where geometry and quantum information are two languages for the same underlying reality. The Entropy Horizon Paradox becomes less a riddle about something exotic in space and more a testbed for how nature preserves coherence when gravity is a player, how entanglement weaves structure into the cosmos, and how the impossible becomes plausible when we abandon old pictures of information as isolated, unconnected. The stakes are not merely academic. They map the path toward a quantum theory of gravity, a unification that can explain everything from early universe cosmology to the way a single photon narrows the gap between two distant observers. So where does that leave us here on Earth? It leaves us with a fresh appreciation for the limits of our intuition. Black holes aren't merely cosmic gobblers. They are laboratories for the deepest questions about memory, reality, and how the universe enforces its own consistency. The horizon acts like a ledger, but not a ledger in a dusty vault. It's a living ledger, written by the universe itself, with entries that mingle and reappear as subtle correlations in radiation long after the original event. The paradox is recast from a puzzle of disappearance into a puzzle of emergence. Information persists, but in a form that challenges how we define space, time, and truth itself. If the boundary holds the key to what inside means, then reading the outside world becomes a way of reading the inside, not by peeking behind an invisible veil, but by decoding the language of entanglement that binds geometry to quantum state. In the end, the Entropy Horizon Paradox invites us to see black holes as the ultimate crossroad between two pillars of science. They test the conservatism of quantum mechanics against the enormity of gravity. They force us to rethink what a memory is when time itself is curved. They push us toward a cosmos where information is not a mere bookkeeping habit, but the grammar of reality. If this is right, the horizon isn't an end, but a door. A boundary where every forgotten detail is nudged into existence again through correlation, through holography, through the entangled dance of space and information. If you want to keep traveling this frontier, if you want to hear how the pages of the universe turn in real time, subscribe. The next chapter might bend our ideas of what it means to know something at all.